The universe, chronology, and the Big Bang. The prevailing model for the evolution of the universe is the Big Bang theory. The Big Bang model states that the earliest state of the universe was an extremely hot and dense one, and that the universe subsequently expanded and cooled. This model is based on general relativity and on simplifying assumptions such as the homogeneity and isotropy of space. A version of the model with a cosmological constant and cold dark matter, known as lambda CDM model, is the simplest model that provides a reasonably good account of various observations about the universe. The Big Bang model accounts for observations such as the correlation of distance and redshift of galaxies, the ratio of the number of hydrogen to helium atoms, and the microwave radiation background. The initial hot, dense state is called the Planck Epoch, a brief period extending from time 0 to 1 Planck time unit of approximately 10 to the negative 43 seconds. During the Planck Epoch, all types of matter and all types of energy were concentrated into a dense state, and gravity, currently the weakest by far of the four known forces, is believed to have been as strong as the other fundamental forces, and all of the forces may have been unified. Since the Planck Epoch, space has been expanding to its present scale, with a very short but intense period of cosmic inflation believed to have occurred within the first 10 to the negative 32 seconds. This was a kind of expansion different from those that we can see around us today. Objects in space did not physically move. Instead, the metric that defines space itself changed. Although objects in spacetime cannot move faster than the speed of light, this limitation does not apply to the metric governing spacetime itself. This initial period of inflation is believed to explain why space appears to be very flat and much larger than light could travel since the start of the universe. Within the first fraction of a second of the universe's existence, the four fundamental forces had separated. As the universe continued to cool down from its inconceivably hot state, various types of subatomic particles were able to form in short periods of time, known as the Quark Epoch, the Hadron Epoch, and the Lepton Epoch. Together, these epochs encompass less than 10 seconds of time following the Big Bang. These elementary particles associated stably into ever larger combinations, including stable protons and neutrons, which then formed more complex atomic nuclei through nuclear fusion. This process, known as Big Bang nucleosynthesis, only lasted for about 17 minutes and ended about 20 minutes after the Big Bang. So only the fastest and simplest reactions occurred. About 25% of protons and all the neutrons in the universe, by mass, were converted into helium, with small amounts of deuterium, a form of hydrogen, and traces of lithium. Any other element was only formed in very tiny quantities. The other 75% of protons remained unaffected as hydrogen nuclei. After nucleosynthesis ended, the universe entered a period known as the Photon Epoch. During this period, the universe was still far too hot for matter to form neutral atoms, so it contained a hot, dense, foggy plasma of negatively charged electrons, neutral neutrinos, and positive nuclei. After about 377,000 years, the universe had cooled enough that electrons and nuclei could form the first stable atoms. This is known as recombination for historical reasons. In fact, electrons and nuclei were combining for the first time. Unlike plasma, neutral atoms are transparent to many wavelengths of light, so for the first time, the universe also became transparent. The photons released when the atoms were formed, and these can still be seen today. They form the cosmic microwave background. As the universe expands, the energy density of electromagnetic radiation decreases more quickly than does that of matter, because the energy of a photon decreases with its wavelength. At about 47,000 years, the energy density of matter became larger than that of photons and neutrinos, and began to dominate the large-scale behavior of the universe. This marked the end of the radiation-dominated area, and start of the matter-dominated era. In the earliest stages of the universe, tiny fluctuations within the universe's density led to concentrations of dark matter gradually forming. Ordinary matter, attracted to these by gravity, formed large gas clouds, and eventually stars and galaxies, where the dark matter was most dense, and voids, where it was least dense. After around 100 to 300 million years, the first stars formed, known as population 3 stars. These were probably very massive, luminous, non-metallic, and short-lived. They were responsible for the gradual reionization of the universe between about 200 to 500 million years and 1 billion years, and also for seeding the universe with heavier elements, heavier than helium, through stellar nucleosynthesis. The universe also contains a mysterious energy, possibly a scalar field, called dark energy, the density of which does not change over time. After about 9.8 billion years, the universe had expanded sufficiently so that the density of matter was less than the density of dark energy, marking the beginning of the present dark energy-dominated era. In this era, the expansion of the universe is accelerating due to dark matter.